Our next task is to do a computation, which is a confidence interval for the population proportion. And what that means is this. In principle, what we have is a population of success-fail. That is to say, this is a binomial setting. And so we have n, which is the number of trials, and then we also have x, which is the number of successes. And so the question is, if we have a certain number of trials, and of those trials we have a certain number of successes, can we use that information about the sample to glean some information, cast that back to the population at large, and glean some information about what we believe is the behavior of the population at large? Now, of course, in that process, there are certain levels of uncertainty, but the uncertainty is, for our purposes, will be handled using the notions of probability. And so, the idea, as when we worked with the confidence interval for the mean, the basic idea is, again, straightforward. We know the population proportion, P. This is the population proportion of successes. For the population, we use the symbol lowercase p. For the sample proportion, now of course these are both of success. The sample proportion is p. The technical word is a caret. This is called p hat. P hat. And so, just as when we dealt with the normal curve, we can have the sample proportion and the population proportion. Now we're going to be dealing with confidence intervals with the sample proportion of success and the population proportion of success. Of course, if we have population proportion of success is lowercase p, then the population proportion of failure is lowercase q. And of course, we know that q is given by 1 minus p. So, we don't need to be given the value for q. If you know the value for p, then you can compute the value for q. Well, similarly, if we have the sample proportion of successes, then we also can have the sample proportion of failures, which is represented with q hat. And in exactly similar fashion, the value for q hat does not need to be given. We can compute it using p hat. Q hat is 1 minus p hat. So anytime we need q, we can find it because if we know p. Anytime we need q hat, we can find it if we know p hat. And then the other important piece of information is what we remember from before. P hat is given by number of successes. X is the number of successes. Divide by the number of trials. N is the number of trials. So, in some problems, you might be given p hat explicitly. In others, and this is actually more commonplace, you're given the number of trials and the number of successes from which you can compute p hat. And then if you need it, you can also compute q hat. It turns out we are going to need q hat in our formula. Now, again, the basic idea is this. We know that the value of p, the population proportion of success, for any experiment, anytime you have a population that's binomial, then the proportion of successes is a number. It does, at least in theory, exist somewhere, and it must exist on the number line. And we know something about p that we didn't know about mu, the population mean. We do know that this is a probability. And so we do know that the lowest value this could even theoretically be is 0, and the highest value it could even theoretically be is 1. So we know the population proportion of success must be a decimal value, or fraction value if you will, between 0 and 1. It must be a value that lies between 0 and 1. Conceivably, it could equal 0, it could equal 1. For the work that we will consider, that will not be occurring. And so we need to find an estimate. Now, again, the basic idea is as before. we can compute the behavior of the sample, and if the sample is representative of the population, then when we find p hat, let's suppose in a problem that p hat falls here. Now, we don't expect the population proportion to be precisely that number, but we would expect that it should lie within a certain margin of error. This is what happens when we have, for example, voter opinion polls. Suppose a community has a ballot initiative, and we want to estimate the number of, what proportion of the voters in the subdivision are in favor of the new ballot initiative. And so typically what you'll see, and you've seen these kinds of things before, you might see in favor, you might see 47%. Now, very often it's stated as percent. We will write this as a decimal. But you'll see 47%. And then what you'll see is down below, plus or minus, and it'll be something like this, 3.5%, or it might say plus or minus 4%. For ease of computation, let's just suppose it's plus or minus 4%. Again, 4%, we would express that as 0.04. What does that mean? What does it mean when we say 0.47 plus or minus 0.04? Well, that means the same thing as it meant when we did population mean value. If we're saying 0.47 plus or minus 0.04, then what we're saying is this value is p hat. That is the 0.47 plus 0.04 minus 0.04. That is the margin of error around this sample proportion. And so when we write 0.47 as just a random example, plus or minus 0.04, that's the same thing as saying 0.47 plus 0.04 and 0.47 minus 0.04, which we could say is 0.47 plus 0.04 or minus 0.04. What would that give this number to be? 0.47 plus 0.04. Well, 47 plus 4, I believe that would be, if I can do my arithmetic correctly, 0.51. And subtract 0.47 minus 0.04 is 0.43. So we would say, let us suppose that this was, and again, I'm just making numbers up out of the blue. So let's just suppose that this was a 90% confidence interval. Then again, this is a very crude interpretation. But the probability, we don't know where p falls, but we know that we would say that the probability that this interval covers the population mean is 0.90. There's a 90% chance. Again, this is extremely crudely speaking. There's a 90% chance that the population mean falls somewhere in this interval. And so what we're going to do is figure the nuts and bolts of, given information like this in a specific setting, how do we find this value, how do we find this value, and how do we construct this confidence interval? So that's going to be the topic for our next couple of videos.